Hi, good afternoon, everyone. I'm Julia. I'm a postdoc at the Wellman Center for Photomedicine, and today I'm going to present a new imaging technique that we developed, and I'm going to show you some preliminary results that shows its potential for skin cancer detection. So the name of the technique actually changed between the abstract submission and now, and the official name is Full Field Amplitude Speckle Decorrelation Angiography, or in short, FASDA. And in order to understand how FASDA works, do you have a pointer? No. It's useful to understand the concept of speckle. So when we have a coherent light source, like a laser, that illuminates a tissue, like the skin, some of the photons get absorbed, some of them get scattered, and speckle is generated from the random interference of the light that is backscattered. Now, if we have a camera, as shown in the drawing, we can record the speckle pattern that is generated from the backscattered light. And the interesting thing is that if the particles that generate the light are static, the speckle pattern will not change. But if they're moving, like in the case of blood vessels, the speckle pattern will fluctuate. And if we analyze the spatiotemporal statistics of these fluctuations, we can gather information about flow. Now, this is not a novel concept. There are several imaging techniques that are based on speckle, and two very common ones are laser speckle contrast imaging and dynamic light scattering imaging. Laser speckle contrast imaging is based on evaluating the contrast. So from the speckle frames, we get the standard deviation and the mean intensity, and the contrast is just the ratio between the two. It requires long exposure times, it can image wide field of view, and it does not require any expensive equipment. On the other hand, dynamic light scattering imaging is based on a more complex processing, which starts from the evaluation of the second-order autocorrelation function, and it requires very short exposure times and super high frame rate, which means very expensive ultra-fast cameras. And also it can image only small fields of view, so it requires a long time to image wider areas. But it can provide additional information about the scatterers, like the scattering dynamics. However, actually so far, as we know to the best of our knowledge, all of the speckle-based techniques are actually 2D imaging techniques, so they cannot provide any depth information about the image vessels. What we propose is a technique that is somewhere in between the two, but with additional features. And in particular, we propose a technique that can provide depth information about the imaged vessels. And basically, we can classify the vessels into two depth categories, superficial and deep. We work at an intermediate exposure time. We use polarizers to enable polarization control. And we simultaneously evaluate two metrics, the blood flow index, which is a common metric in laser speckle contrast imaging, and the adaptive speckle decorrelation index, which is a metric that we developed, and it is based on the second-order autocorrelation function. So the device that we developed is wide field. We are now imaging an area of 1.5 centimeters in diameter, but we can actually expand it. It is very fast. We only require 4 seconds to acquire the data and less than a minute to process it. And it works regardless of skin pigmentation, since we chose to use a near-infrared laser source. And at the same time, we avoid increasing the cost of the device by using a black silicon camera, which is a new type of camera with respect to indium gallium arsenide, which is what you usually need to image in the infrared or near infrared. So we use this device to image different lesions. This is an example. You can see the white light image of the region and 2 sample speckle frames as recorded by the black silicon camera. And then you can see the OCT AMFAS view of the area and the FASDA images that we get, so the one evaluated with ASDI and the one with BFI. And the blood vessels that we can image with ASDI are around up to 500 micron deep, while the ones that we can evaluate with BFI are between 500 and 1.2 millimeters. And actually, you can see highlighted in white vessels that are too deep to be imaged with OCTA, but that we can image with FASDA. And lastly, this is an idea, shows an idea that we have as this device could be used for skin cancer detection. So here we image 3 different areas. One is normal skin, and then a benign nevus, and a dysplastic nevus. And you can see from the 3rd column how the vasculature, the superficial vasculature that is revealed with FASTA is actually very different, both from the surrounding skin and also from another normal skin area, but most importantly from the benign nevus. So we are now in the process of starting a pilot study on skin cancer patients, and in order to explore these capabilities further. Oops. Thank you.